All right, so we're going to continue on with our discussion of Lagrange multipliers as a method to finding min-maxes on surfaces subject to constraints of other surfaces. And so let's see, we were kind of working on this problem last time where it was just find the points on the hyperbolic cylinder. So they use cylinder when like one of the components is free. In this case, y is a free component, meaning that y can kind of go on forever in one way. It doesn't actually mean like the cylinder and maybe the sense that we're used to talking about cylinders. What we try to do here is we try to regard x and y as independent variables. So if we did that, then we like set z squared equal to x squared minus 1. And then we rewrote this h of xy, which was this f of xyz function, x squared plus y over z squared. We replaced z of x squared minus 1 and got this function. We took the partial derivatives, and then we got that 0, 0 was a critical point. However, we kind of like ran into this issue because there are no points on the cylinder where both x and y are 0. If we go back here, for instance, we can't have x equals 0. That's just not on this constraint. So what happened? What went wrong? And so the first derivative test did everything that it was supposed to do. It looked at this function h that we made, which depended on x and y, and it said, okay, this is on this function h. We're trying to find a min or maximum value, and it found that there would have been a min or max at 0, 0 of a value of like what, 1 or something, or minus 1, I guess. So what went? So what? What did I want to say here? I wanted to say one more thing here. So like, so although here, let's just say this, and although the domain of H is the entire XY plane here, we don't, let's just say, want to include the band. So this is like this little band right here. The band between x equals 1 and x minus 1. So what this kind of shows you is that like doing it this method, you have to be like really careful about these sort of things, and you have to like go back and actually check, does this critical point that I got actually make sense? And if it doesn't make sense, then you kind of have to like rewind. And the very first assumption that we made is we regarded x and y as independent variables. And I think that was the original problem here, because in x squared minus z squared equals 1, like x technically has some restrictions, so that aren't going to show up in h. However, z on the other hand really doesn't have any restrictions. Like we could plug any value in for z and find a corresponding value for x, right, to make this quantity 1. But we can't do the same for x, right? Like we can't just like plug in some random value for z, like I mean, we can't just plug in some random value for x and then find it in a, for example, we can't make x 1/2 and then expect to find a z, right, to make this equal to 1. So instead, now we'll like jump to attempt 2 here, and we'll do this on the back because we kind of ran out of space.
It was between x equals 1 and
right, and minus 1, like, right, so like the entire, we don't want to include this band, right? But we can kind of get around this here by, so attempt 2 here, we can avoid this problem. This time, let's let's treat this time y and z here as independent variables instead. And we shouldn't have this problem anymore because there really isn't any like restrictions on z this time, like there were these restrictions on x. So if we do it this time, so this time we're going to set x squared equal to z squared plus 1. And we're going to substitute this time into f of x, y, z equals, what was it, x squared plus y squared plus z squared, because it was the distance from the origin. But we're not going to do the square root. We're just going to do the distance squared because that's easier to manipulate and whatnot, right? So last time we were talking about that, how we can minimizing the distance is the same as minimizing the distance squared. So all right. So so this time let's call it k this time. So k of y z with this substitution now is going to be z squared plus 1 for x squared, right? And then plus y squared plus z squared, or 2z squared plus y squared plus 1. Okay, so so now we're going to kind of do the same kind of thing here, where we take the partial derivatives ky and kz here. So ky is going to be 2y, and kz is going to be 4z, and we're going to set these equal to 0, and that's going to give us that yz is equal to, wait, let me just make sure that this is right. Yep. So this is going to be 0, 0, and so now if we so what does this lead to this time? Well, so this time this using that leads to so if we have that x squared here is equal to, and yz is totally okay, like that's that's totally a point to where that's on the that is on this cylinder x squared minus z squared equals 1 this time. So we don't have the same problem as last time now. And so this leads to x is equal to, what was it? Our x squared was z squared plus 1, which is 0 plus 1. So that gives us that x is equal to plus or minus 1. And if you kind of look at this picture here, like this kind of, this is x here. This makes sense. And this is really what we would kind of, just by looking at the picture, like this is really what we would expect to, because like here, like the distance from the origin, it's kind of clear that, you know, because of this thing is like of this geometric shape, that 1 and minus 1 should be, x equals 1 minus 1 should be these points that are where the minimum is, right? So, okay, so what else do we need to do here? So the corresponding, so this leads to, this gives the points plus or minus 1 for x, and then 0 for y, 0 for z on the cylinder. And we can also see, we can make this argument that k of y comma z, which is this thing we're trying to maximize with this, you know, with x squared being z squared plus 1, right? This is going to be equal to 1 plus y squared, we said plus 2z squared, and we can see that because y squared and z squared here. So this is like, what we're doing now is we're trying not to use the second derivative test if we don't have to right now. But we can just notice that this is definitely always greater than or equal to 1, right? So what else? What are we trying to say here? So, right, so we can be sure. So we know that plus or minus 1, 0, 0 does indeed give minimum value for k here. with minimum, let's just write one more thing here. Minimum distance being 1 unit. So the minimum distance here is 1 unit. And anything else I want to say about this? Let me think real quick. All right, so this is kind of like this is kind of like building off again from basically the stuff we did in 13.7, extreme values and saddle points. But now we're going to kind of like go through. So we've done 2 attempts at this problem. First attempt didn't work well, and we tried to point out, you know, why it didn't work correctly. The second attempt is, again, kind of like from the methods from the previous section. So now we're going to actually kind of like, before maybe introducing Lagrange multipliers.
So I'm kind of confused as to where the x squared plus z squared, or x squared equals z squared plus 1, and like, where does that come from?
Where does that come from? So on the original problem, it was find the points on this cylinder that are closest to the origin.
Okay.
And so the function that we're trying to minimize is x squared plus y squared plus z squared, since that's like the distance squared to the origin.
Yep.
And so here I just set, so here the z squared equals x squared, the x squared equals z squared plus 1 just comes from solving that
Okay.
right here.
So why can we solve that one but not the one before?
So the issue was when we regarded x and y in the first case as independent variables. What happened was that's like in this function that we then made, that came from this, like you could plug in any value of x. So when you do the partial derivatives, you get a minimum value that wasn't originally now on this.
Yeah.
That wasn't on this hyperbolic cylinder thing. All right, but and so that's a problem, right? So that's just giving you a solution that's not that's not compatible. On the other hand, like instead of having x and y be independent variables, like now z on the other hand, you could plug any number of this and find a value of x that will work.
How do we know that?
Just give me a z value and set x equal to the square root of that. Like you could, okay. So
Like, why does it work for z but not x?
okay. So if we were to solve for z here, so if I give you the value 0, tell me what value of z works.
Like 0 for x?
Yeah, 0 for x. You'll find really quickly that there's no value for z that works.
Yeah.
Right? So that right there is like the issue, right? Is that if you think of x as an independent variable, then it actually has restrictions on its domain like that.
Okay,
Like there's
so
certain values of x that you just can't plug in, like things between z -1 and 1.
Okay, so we need to make x dependent.
Yes, and z be and instead make z be the independent variable instead of x. So in attempt 1, we made x and y independent variables. In attempt 2, we made y and z instead of x, we made z the independent variable.
Okay,
And because there was no other there's no other restrictions on z, then we were able to we were able to then find the right then here we were able to since there's no restrictions on z, we can just take whatever we get from the partial derivative set m equal to 0 as our correct as a correct solution this time.
Okay.
Does that make sense? So so like that's one thing you want to kind of look for, like if you're doing it this way, is if I'm going to make this, if I'm going to solve for this variable, can I plug in any variable for it, right? So if I'm going to solve for z here and make it in terms of x, can I plug in any value of x? And the answer is no. But if you write x squared in terms of z, you can plug in any value for z.
Okay.
Okay. So, but now we're going to kind of like go into like a second kind of solution. And so this solution is not going to make as much maybe sense at first. So it's going to take some discussion to kind of understand maybe like what exactly is going on. So in this picture though, we're now kind of thinking of this x squared plus y squared plus z squared minus some a squared equal to 0, this sort of sphere. And then we have the x squared minus z squared minus 1 equals 0. And we're kind of like looking at, in a sense, like where these are going to like touch and where their tangent planes, I guess, is going to be parallel, is kind of like what we're kind of, and that's really, I think the key there is that the tangent planes are going to be like, pictorially, they're going to be like parallel at this place where this quantity is minimized or maximized. So what we're going to do here is we're going to set this time, so we're going to set f of x, y, z this time as x squared plus y squared plus z squared minus a squared. So like we're thinking of it as being like equal to a squared, so like equal to 0, and g of x, y, z equal to x squared minus z squared minus 1, and so what we're kind of noticing here with this picture is that the gradients, delta f and delta g, which remember that these gradients are like the pointing like orthogonal to the tangent plane at any particular point. Like, so when we make the tangent plane, like the gradient vectors are the, at evaluative points are like the A and the B and the C and the AX plus BY plus CZ. So the gradients delta F, delta G here will be parallel here, where the surfaces touch. All right. So at any point of contact, we should then point. So when they contact, when they come into contact. So at some value of A, for example, like they're going to come into contact here. And we found this A to be 1. We already kind of know this A is going to be 1 from our previous solution. But when they do come in contact, so when they contact, we should have that where the surfaces will be parallel where the surfaces touch. And when they, sorry, I'm just trying to make sure I'm saying what I want to say exactly. When they contact, there should be some scalar lambda such that, so like we should have that these tangent planes are parallel at this point. So we should have that the gradient of f is lambda times the gradient of g. So if we solve this equation here at this point, then so the gradient of f is going to be, or let's see, 2x, 2y, 2z, this one equals lambda, and then the gradient of g is going to be 2x, comma, 0, comma, minus 2z, minus 2z. So this gives us 3 equations here. This gives us 2x equals lambda times 2x, and it gives us that 2y is equal to 0, and it gives us that 2z is equal to minus lambda 2z. So now we want to ask, okay, so for what value of lambda whose coordinates satisfy these scalar equations? So now we want to ask, what values of lambdas will a point x, y, z satisfy this constraint? When will these satisfy? When will these satisfy that x squared minus z squared minus 1 equals 0? So we know that from here, what do we know? We know that x cannot be 0, right? So if we use that knowledge that x cannot be 0, then which one of these equations, like what can we do? If x is not 0, which one of these can we simplify and say what lambda is? So like on this one, z could be 0, so we can't just like cancel the z's so quickly. Does that make sense? But on this one, we could, because on x, we already said that, you know, x can't be 0 here, right? So we could then simplify this, right? We can simplify, so we can simplify here. 2x equals lambda 2x to 2 equals 2 lambda, or lambda equals 1. So for lambda equals 1, so that now if lambda equals 1, then we have 2z equals minus lambda 2z, right? So that gives us that, what? That gives us that 2z equals minus 2z. Right, and so what? So if 2z is minus 2z, what must z be? So if 4x is minus 4x, or if x is minus x, what must x be? 0.
Oh.
Right.
Yeah.
So this gives us that z is equal to 0.
I was like, I can't remember.
Yeah.
No real number? I don't know.
So now we're at points of the form. So we've narrowed it down now in some sense to points of the form x 0, 0. So now we're just going to plug it now. So now we're going to plug this into, so if we have x squared minus z squared equals 1, right? And this is going to give us x squared minus 0 squared equals 1. So we're going to get that x is equal to plus or minus 1. And so therefore the points on the cylinder closest to the origin are plus or minus 1, 0, comma 0. So this kind of gives, okay, so like it's a little bit wordy here, what we wrote, but so what did we kind of note here? We noted that like if we kind of rewrote this f of x, y, z like this, and this gradient like this, then at this, this minimum distance is going to happen at this place where this sort of sphere intersects, or this sphere intersects at some radius a, intersects these hyperbolic cylinder, these wavy things, and when they do touch, we're going to have that the tangent planes should be exactly the same, which means that the normal vector for these tangent planes should be scalar multiples of each other, which means that the gradients should be scale at these points should be scalar multiples of each other. So we kind of like did this weird thing where we inserted this extra variable lambda and we sent them equal to each other, and then we figured out what this lambda could be, and we use that to kind of figure out what, and we use that and the original constraint that x squared minus z squared minus 1 equals 0 to kind of narrow down exactly then what the x and y and z should be. So we don't have, so some of the benefits of this is that when you get into like even like higher variables, like this becomes like the go-to sort of way, because it kind of eliminates the most work, and it makes it, and in like on a computer kind of programming perspective, it eliminates the most amount of work and gives you like the most efficient computability time as well. But it's also easier like on paper in many cases to kind of do it this way as well, especially when the equations get like really complicated.
And we know x can't equal 0 because of the last problem we did?
Because x can't be 0,
Or
because it's just not in the domain of this function of this.
Okay.
It's not in this set of points, right?
It's because if you plug, so like in another way is like to say it is if you plug 0 in for x, you create an equation that's not solvable.
Not solvable in the real numbers.
Well, no, real.
Yes. Yeah. Right. Okay. So before kind of like doing more examples like this, let's we're going to do some proof type things and try to really kind of understand mathematically, maybe at least try to understand mathematically what is going on here a little bit. So the solution to example 2 here, we use the method of Lagrange multipliers. So this method says that the local extreme values of a function f of x, y, z, whose variables are subject to another constraint, g of x, y, z equals 0, are to be found on the surface g equals 0 among the points. So these local min, local maxes are going to be found at these points where delta f is a scalar multiple of delta g. So to explore this method further and see how it works, we're first going to make the following observation, and we're probably going to, this will be one of the few times we'll probably do a proof in this class. Let's see. So let's try to read this and try to understand what it's saying. So suppose that f of x, y, z is differentiable in a region whose interior contains a small curve. Okay, so we have this f of x, y, z, which is this kind of like volume, three-dimensional volume in 4 space, really. And inside of it, we can like make little curves, these little one-dimensional curve type things, like on the surface. And so this is one of these one-dimensional curves, the C. Okay, and so it contains a point. Okay, so if P0 is a point on this curve that's on this surface, where f has a local maximum or minimum relative to its values on C, then delta, this gradient of f, is orthogonal to C at P0. So this is kind of like this level curve sort of argument, where when you make these level curves, the function is not changing at all, so the gradient, so the derivative is 0. Okay, so let's see if we can, let's see how this works. If we wrote here, so we can say, so we want to show here, like let's do like a little proof thing. So we want to show that delta f is orthogonal to C at P0, right? So we can first think of f as being, instead of x, y, z, now it's these x, so f of, this is f of, for example, x of t now, y of t, and z of t. And so if we were, so this all now kind of like, since we're like parameterizing it on this one curve that just depends on its parameter t, we can think of this whole thing as just being, you know, a function of t. And then we can apply the chain rule here, right? So this is just one variable calculus now. So if we did that, we have df over dt. And now we got to employ the chain rule stuff from chapter 4, which says that this is partial f over partial x, dx over dt, plus partial f over partial y, dy over dt, plus partial f over partial z, dz over dt. Okay, and now we did this kind of in 3.5, something like this, but we also could recognize this, right? The dx over dt, dy over dt, dz over dt, that's just dr over dt, right? And the partial f over partial x, partial f over partial y, partial f over partial z, that's just the gradient of f. And we can think of this as the dot product, right? So this is the gradient of f dotted with dr over dt. Right, it's just this dot product, right? So now at any point p0 where, so notice that in this thing, what are we assuming? We're assuming that f has a local maximum or minimum relative to its values on C. So at any point p0 where f has a local maximum or local minimum, we know, what do we know about df over dt? What is that equal to? Zero, yeah, because it's a local min, local max, right? So this is equal to 0, right? Which also is equal to the gradient of f dot dr over dt. So what does that imply then? So that implies that you know, if the two vectors have a dot product equal to 0, right? That implies that delta f and d, that implies that the, so if dr over dt is is like the slope of the tangent line at that point, right? So that implies that df and r of t are orthogonal. And this works for any curve that's kind of like running through the surface at this point. For every single curve, this is true. Not just like one curve, but any curve. So you can be sure that, you know, delta f is, you know, orthogonal completely, right, to the surface, the gradient. All right. So so we're almost kind of there to like now kind of understanding why to writing this sort of argument. So this theorem 12 is key, right, to understanding kind of this argument for why Lagrange multipliers work. So as a quick, but before we kind of get to that, which is going to be this argument kind of in here, as a corollary, on a smooth curve, let's say you're just in 2 dimensions now, or f of x, y on its local variables, on its local maxima minima relative to its value of the curve. So this is just saying that this is also true in the dot dr over dt is equal to 0. So this is saying that it's also true in the 2-dimensional case. So before we make this whole argument, just one more thing I want to note. Recall also from what was it? I think it was in 13.5. One of the things that we also kind of noted is that if g of x, y, z equals 0, if we have this level surface, which is what we have right now with the g being like the constraint along curve r of t, like before, then one of the things that we found where r of t again is this sort of x of t, y of t, z of t. We have that dg over dt, right, which was this gradient, because g is 0, right? We automatically know that this the gradient of g at, I don't need that, at r of t dotted with dr over dt is also equal to 0. So on a level surface, we also always, like, this is always true. So what's the difference here? Is that this is always true, like for a level surface where you're setting it equal to 0, right? But what we showed here is that if we have just like some surface or volume f of x, y, z, we found that at local min and local maxes, it happens to be true as well, that delta f dot d over dt is 0, right? So like what this is saying, just to be true, right? This is saying that delta f at r of t, right, dot dr over dt is equal to 0. When we're saying that delta f is orthogonal to c at p0, we're making this statement, right? That, and that's what we proved. This is also in the proof, but right. But it's also just true in general if you have like a level surface, g of x, y, z equals 0, right? Because, but the reason is different, right? The reason that we got 0 here was because we're at a local min or local max, right? The reason that we're at 0 here is because g is 0, so dg over dt is 0. So different reasons, okay? So what does all this mean? So now we're just gonna write a little bit in here, right? So assume here, so we're gonna kind of continue and get to this, okay? So we're going to assume here that, again, f of x, y, z, g of x, y, z are differentiable. That's one of the assumptions. And then we're assuming that P0 is a point where both, where g of x, y, z is equal to 0 and f has a local min dash max, right? So we're assuming both of those, right? We're also assuming here that delta g is not actually equal to the 0 vector simultaneously at any point on g of x, y, z equals 0. Then what we can say here is that, and with all of this being true, that means that f then takes on local min dash max at P0 relative to its values. And so here's the key takeaway: relative to its values on every, not just one, not just two, but like every differentiable, so I'll just use diff or differentiable curve through P0 on the surface. So now I'm repeating this. So on the surface, g of xy equals 0. Okay. So now we're here. All right. So these are like all these assumptions, right? So just think of just try to like this is like one of the more deeper things that we've probably gotten to in this class. So do spend some time to like wrap your brain around this. It's not, I don't know if this is something that you can fully really kind of get just in one classroom, just in one class experience, no matter how good a teacher is. Say it again, what were you asking?
I was gonna ask, is that supposed to say g or del g is not equal to the 0 vector?
Yeah, it's not equal to the 0 vector.
Okay.
Yeah. Because then this whole like setting like delta f is lambda, delta g doesn't work very well if it's the 0 vector. Okay, so yes, question. What? Oh. Yeah, I'm just repeating now this right here. So on the surface g of x, y, yeah. So, okay, so on every single differential curve through P0, f takes on, right, this local min, local max at P0, right? So therefore, delta f here is orthogonal to the tangent vector of every single differential curve through P0. But also, it's not just that that is true for every single curve, for every single possible curve. It's also true that that because g of x, y, z is 0, it's a level surface or a level curve or whatever you want to call it, right? You also get that this is true for this, right? That that delta g is also orthogonal, but for different reasons, right? Not for the same reason, not because it's local min, local max on f, but because it's a level surface that's equal to 0, right? And so any kind of curve that goes through it is going to satisfy dg over dt is 0, and you're going to get this orthogonality, right? So, so moreover, so what does that mean? So if both the gradient of g dot d over dt is 0 for any single curve r, and the gradient of f dot d over dt is 0 for any for any curve R, right? Then the only, and it doesn't matter whether you come from, you know, this direction on this curve or this direction on that curve, right? You're gonna get, like, they both give you 0, right? And so the only way that this dot product can like make that work, where you get 0, no matter like what kind of inputs of R you put in. You could put in very different, you could come from very, very many different directions on this curve, right? So it's those, these are the reasons why delta F becomes a scalar multiple of delta G, right? Is because they both simultaneously, when dotted with dr over dt, become 0, where R is any curve through both of these surfaces, right? Right? It's just the only way. It's the only way that you could get 0, right? So basically, you know, this is always orthogonal g over dt, no matter which curve you pick. That so is delta F always orthogonal g over dt. And so the only way that you can have that be simultaneously true for every single curve is if delta G and delta F are scalar multiples of each other. And so, and it's a pretty deep result. I would put it, I don't know, I'd put it on par with, I don't know. It's probably the deepest result we've kind of come to in this class. And it's something that when I was trying to like teach it, like when I was like, I had to spend a good, you know, hour or two myself just thinking about how I wanted to say this to you guys as an example, because it's really, because it's like, it's hard to not just understand, but also explain, you know, like, but yeah, but that's kind of like the idea here. So I don't know, it doesn't, I feel like it's very hard to kind of intuitively capture this, but I feel like maybe this sort of like picture right here of you kind of making these two different surfaces and setting them equal to kind of like 0 and seeing where they intersect also kind of gives them more of like a geometric kind of explanation to why gradient of F is lambda as scalar multiple of the gradient of G. But anyways, I don't know if I'm probably close to being out of time, but I think we could do one of these real quick. Well, let's at least get started on one of these, I guess. Let's see. Yeah. So what's this new strategy that we picked out? So find the greatest and smallest values of the function f of xy equals xy takes on the ellipse x squared over 8 plus y squared over 2 equals 1. So this is an equation for some kind of ellipse with some semi-radius. I don't know, it looks something like this right here. So in this case, so what we want to do here is we want to first kind of rewrite, we want to make our g of xy here. So we're basically kind of always doing this thing where it's like x squared over 8 plus we just take whatever's on the other side of this constraint, move it over, set it equal to 0, something like that, right? And we want to now try to solve here. The gradient of f equals lambda times the gradient of g. So if we do that, that's going to give us, and okay, so we need to make sure that, we need to make this clear, and we need to make sure that whatever we kind of get here, that it satisfies g of xy equals 0 as well, right? So we got to kind of have to keep both of those, keep track of both of these. So the gradient of f equals lambda gradient g. So let's see, we're going to get x over 4, no, here's gradient of f, right? So the partial with respect to x is y, the partial with respect to y is x. So we're going to get y comma x here is equal to lambda, and then what else? X over 4 and y. Oops. Does that look right? X over 4 and y times lambda. So this gives us a couple different equations here. It gives us y equals lambda over 4x, and it gives us that that we need to try to solve, and it gives us that x is equal to lambda y, And then we also have this other equation for the ellipse that would kind of make sure that these things are on. So I think this is a good stopping point. We will continue on with this next time.
So what part of it's confusing? Is it the part that's like?
It's understanding kind of like why this should even work in the first place, this sort of method, which we haven't really even got to yet too much. I mean, you did one example, but we need to do more examples. But just that setting the gradients equal to a scale of multiples of each other, I feel like that's confusing why that would even work in the first place. Because it's not anything like you did in Calc 1, right? Like this is totally like, this is like totally removed from Calc 1 now.
So the confusing part is why the gradients are scaled.
Yes, that's the confusing part.
Okay. Because I was like, I understood that, but I didn't understand the other parts. So
Right.
So, okay, that's what I. Okay.
So after like understanding that, then these problems should be a little bit easier to do, these next few.
Hi, we just have a question on, so if you get it above an 80 or 90,
Yeah.
what percentage are you getting back for questions you have?
If you retake it.
I haven't fully decided yet, but probably like, I don't know.
Because on the sheet, it says you get
Yeah,
50.
like 20 to 50%, somewhere in that range.
Because like
20 to
technically to
50%.
someone who does like, it's like a 79 or gets the full 50
Oh,
back,
it'll
will
be-
they never get
No,
above us?
no, it won't get above you. No,
Okay.
it'll be like slowly kind of incremented.
You know, if you think about
So
it,
I'll make a function that kind of like decides how much you get back based on your score.
you know, technically,
That makes sense.
the 50% is progressive by itself.
But no, someone
because-
who got like worse than you will not be able to have a higher score than you.
Okay, that's what we were just wondering.
Okay,
'Cause
yeah,
we
no
were like
problem.
figuring out math and we're like, dang it, we should have scored a little less. You get a little more.
Oh, no,
Thank
yeah.
you.
Yep, no problem.
It's fine, you know.
What was that?
No, you know, with the grading systems, like, it doesn't matter how, you know, like, as long as you get a good grade, doesn't matter what else comes.
What?
So, like, with the percentages, like, if you go
Oh.
like a 90, then the possible is 5 points back, right?
Mm-hmm.
Half of it. And so that's less than anyone who scored lower will ever get, but it's still higher.
Yeah.
So 50% would be good for everyone, because even the higher you get, the less you will get.
I see what you're saying. This is this is like, instead of just giving, okay, so another way of looking at this is I'm just trying to do it in the fairest way possible, I guess. What I perceive, I'm trying to kind of find a way to keep the grades fair, like at least for now, like a little bit more homogenized. Give people a chance who struggle at first to kind of like to, you know,
Yeah.
to yeah, because sometimes you just like have a few sections that you struggle with a lot, and it's just those particular sections, and then you're like good the rest of the course. And I don't think that should cause you to have the difference between like a B and a C.
I mean, that's how. I mean,
Yeah.
that's how that's how I felt about like that first kind of just. I was figuring stuff out, but then like when I did the homework for the past 2 homeworks, I didn't have to look at my notes hardly at all.
I haven't decided yet.
Okay.
Sorry, I didn't mean to interrupt you. He was kind of like, I was getting 2 people talk. Do you have to do these 3?
Oh,
Did you do? No.
oh, well, that's nice. Too.
Yeah.
I already did them. Oh,
Okay, well, it's good anyways.
So is it essentially like this, where you know T is 0 because if you plug 0 in, you get that point, right? So then,
So here's your thing, right?
like, okay.
So now
I'm
you
trying to
just look at the multiple, at this point, once you get to here,
Mhm.
you just look at the multiple choice, right? And one thing you notice right away is because you have a 0 in this coordinate, right?
Mhm.
Your answer in the first coordinate has to be a 2.
Mhm.
And so that narrows you down to like 2
Yeah.
of the multiple choices.
Mhm.
Do you see why?
No, I guess what I see why it does. I guess what I'm asking, I'm just wanting to go through like my
Okay.
thought process for this problem just to confirm that I did it. Cause
Okay.
like, cause I'm more interested in like understanding this than knowing I got it right.
Okay.
Okay, so we know that T is 0 because when you plug 0, the only way to get 210 out of R is to plug in 0,
Yeah.
right?
Yeah.
And then this is the equation of a tangent line through that point.
Yep.
So this is the initial point.
V is R prime of 0. Right.
Yeah, you just derive it, and then
Yep.
it's R prime is 0 because
Or V of T if you want to call it V. That's fine too.
yeah, okay.
Yeah. Yeah.
But then this technically depends on a different parameter than this.
Exactly.
Okay, that was the part I was confused about. I thought
Yeah.
they depended on the same thing.
No, not at all. Because I mean, this parameter is parametrizing this weird curve T, right?
Mhm,
Which is just going wherever it wants to go, right?
mhm.
While this one is parametrizing a line, a tangent, the line that's tangent to the
Okay,
curve
yeah.
at that point, T equals 0.
Oh,
So at T
okay.
equals 0, you need to make an equation for a line, right? And it doesn't really matter. Like, you think of these T's and S's as just like dummy parameters,
Yeah,
right? They're not like, they don't inherently mean anything. They're just being used to
yeah.
allow the curve to go from one spot to another.
It's like if you have a function of x, y, z, and you have x squared equals a, y equals 2a, z
Yeah.
equals 3a. Well, if you have x, y, z of this,
Yeah.
and a is okay.
Yeah,
It's kind of like
it's
okay,
kind of like that.
that makes sense.
And there's more than one parameter you can use. Like you could replace T of T plus 1,
Okay,
like especially in the tangent line, right?
okay. I guess that was the part I was confused about. Is it's a different parameter because this
Yeah.
is parametrizing a line that's tangent at that point.
Right, exactly.
Got it.
Yep, yep.
That makes sense. What was I